we have a larger patches. It's basically set in a little box that says diagnostics paper. Yeah. So I think that's also a very common paper that's accessible for, in terms of if we are going to on the path of using separation, any amount of fluidics that we will do with the set of paper. And then we move into the realm of synthetic paper. This feels very much like regular paper, but I'll let you guys come up front and start touching each one of these. But this is actually many different types of plastics. This was invented primarily because people didn't like their money to be soggy, because other people wouldn't take it. So in many tropical countries, it became a very valuable thread. Australia sort of started that, and then now a lot of currency have transitioned now to what is called synthetic paper. It's very valuable as a designer to play with. So there are many versions of these, and you'll kind of see that there, again, many types of thicknesses. For anything that you're trying to really do that's waterproof, it's actually quite valuable. And then finally, there's also metal. So this is copper sheets. We use these sheets for a lot of things, making compliant circuits, encoding a lot of function on these papers itself. So if you haven't played with this also is in a form of, I'll talk about tapes in a second. And then this is what I meant. This is actually a metal. This is shim stock. You'll see, you can actually do and build things out of this as well. And shim stocks are very valuable for just general applications. But again, it's also useful for you to think about, try making the same thing out of this, and you'll get a sense for how the bending scaling actually works. Finally, there is also some, this is primarily from photography. These are called gel papers. This is used as diffusers. So lots of really fun optics properties, but also Mylar is used. I can't find Mylar, and I think somebody mentioned that PRL might have Mylar, So yeah, we should maybe at some point of time when we take a break, we can think about getting Mylar. That's also another very valuable thin sheet that we use in projects. And then another one related to all of this is Kapton. So I don't know how many of you have seen Kapton before. This is really what makes all of the space industry work. So this is called Kapton. It's incredible in its thermal resistance. So when you're thinking about trying to make something that's going to be thermally very stable over long periods of time, lots of flexible circuit boards are all made on Kapton. So when you think about these ultra thin flexible electronics, they all have a Kapton layer on it, because when you're trying to get solders and other things and high temperature things operating, this is really an incredible compound. And also it cuts really well with a couple of different types of lasers. I think another roll of Kapton, and I think there should be a roll of copper somewhere. Yeah, so this is that roll of copper. So this is fun and useful when you're starting to make circuits and other things that are completely compliant. I could go on and on. I mean, tapes are another example of that you can start. Of course, I have some Post-its here, and the kind of exercises we'll try just doing today is for people to get a little bit familiar with these materials. There is a broad range of things we can do collectively and also just in groups itself. And I'm just hearing from Pierre that Kapton is common in 3D printers itself. Pierre, did you mean to say that it's been used as a material to print with, or just to keep things to be stable in a 3D printer?
Yeah, the second one.
Yeah,
I haven't seen
because I think
as a
Kapton,
material.
really,
Yeah.
I don't know of a printer that can print in Kapton. That would be amazing. But because of its thermal resistance, I can imagine that would have to be very high temperatures. But I think the goal for the exercise today is to just spend some time. We'll just internally, I think we'll break up in groups of 2. You should just discuss what's the most interesting thing you can make in an hour, and then try building that. There are a couple of things that I can give you guys to build there are lots of geometrical things that we can play with, but I think it would actually be fun for it to be much more open-ended in some sense. I think it is valuable. Some of you can really think about structure as a component, but sometimes it's also valuable to say, oh, I have this function in mind. Can that function even be embedded? And I want to have you guys also just be working together on open-ended problems too. And one thing that we can then do is, if you have a specific function in mind, then we'll sit down and say, oh, this might be a place to start. Like, for example, I'll put that out. Something that I'm going to sit and design today with Ian is a type of, like, I think something I've been thinking about as an actuator. How do you make a motor out of paper? I have an idea, but I don't want to, I want to seed it in your head. Can you make a motor out of paper? Something that's going to actually crawl and walk. I mean, there's a lot of things that people have done in all kinds of interesting ways, but try starting with a wild idea that you have. I mean, of course, any of you can fold and make masks out of paper. And I think the thread, we can go down the direction of function. And if some of you who are interested in structure, there is a very large class of YouTube videos around origami. If you have never done it before, it's actually valuable to practice a little bit. I'm hearing paper airplanes. You can start with paper airplanes, but I would want you to challenge yourself a little more. So try making a paper airplane that has some degree of control, for example, like some of its surfaces are warpable, or try adding something more to what you might have thought about before itself. The other thread on this is the classic way of getting started is you can also just fold some exciting classical origamis. So Mira origami is a great example. If you have not done a complex origami before, I'll open up some YouTube channels for people to just watch. Mira origami would be a fantastic one as kind of a, getting into much more of a moderate complexity origami. The other one is hexaflexagons. I don't know how many of you have folded hexaflexagons. If you have not, you're up for a treat. So try setting up. I think maybe as a general exercise, we can all make hexaflexagons so that everybody's kind of warmed up. And then after the warm-up exercise, I'll go group by group, and I think I'll have a discussion both online and with folks in pairs of two. I think all of this is already divided up in some sense. So if the 6 of you can just form groups of 2, that would be a place to start. And I think you can open up your laptops and just do a quick YouTube hexaflexagon, how to fold it, and come out, take some paper, get started. And then we'll go around thinking about, oh, what's the wildest thing that we can make in an hour or 2? And, I think much of this is really about playing with many of these materials so that at the end of the day, you have a sense of what these materials are often capable of. So I'll open up, and anybody who has previously done origami, I know a few sets of folks had mentioned it, or anything that looks and feels like built with paper, they're welcome to share it. I was gonna bring some of the things that I have done. I'll go find them in a second, but I'm curious if folks have something to share as well. I'm gonna try connecting the laptop in the meantime. Anybody wants to share any origami that they might have done in the past?
Yes, sir. Actually, I want to share.
Yeah, go ahead, Ishan. I'll give you
this. I just made a
second.
origami dragon.
Wait for one, Ishan, just wait for a second. I need to connect the screen so people can actually see you. It's always a challenge. Connect it to the right here. Just give me 1 second. And amongst this group, people didn't bring any origami, right? Okay. So let's try connecting again. Okay. So Ishan, you can go ahead.
Yes, sir. So actually, I have made this origami dragon. This.
That is pretty cool.
Yes, it is very cool and very fun to make.
Yeah, so can you talk through it? How did you build it? What does the design process look like?
Actually, just it was made from a square sheet of paper, just folding it and making a particular shapes. There are so many folds in it. If I just open it, so it is quite complex. Like,
All of that effort goes out in a second.
yeah,
Say that again?
like just
No, it's okay.
back to a normal piece of paper.
Yeah. So I don't know if people recognize, do you use the tree maker, Ishan?
No, sir. Actually, I made these on my own.
No. What I meant is, did you use any software at all?
No software.
I see. I'll just show something that's useful. And so how did you design, for example, the sets of folds that you need to get eventually into the dragon?
Actually, first I started with the normal bird, but then I just keep folding and folding. I got interested in it and I just created something new every time.
I see. So this is a trial and error as a process itself. So on Discord,
sir.
if you all look, I will share for our lab session. Is this lab 3, right? Is that correct?
Yes.
I'll share a link for Tree Maker. So there is a lot of, I wasn't going to get into that in a second, but maybe after people have done a little bit of work, there are some phenomenal tools that also help you mathematically think about how do you go from a shape to a skeleton and then back to folding. Ishan, how long have you been folding things?
Like from when I started or just this particular piece?
I see. But this is not, I'm assuming, hopefully this is not your first origami.
Yes, sir.
Okay.
I'm making origami from last 6 years.
I see. Okay. Yeah. So I think, it's fun to see, because if folks that are interested, it's valuable that, you do have to invest time, especially when you're trying to come up with new designs per se. Anybody else wants to share anything that they have folded in the past? I'm curious if already in the on the thread of thinking about things people might have done that are interesting with paper. They don't have to be in the classical phase of origami itself. Okay, so I think one thread that we'll try to do is, at least today, let's make something that's interesting together. So the first thing we will try to make is a hexaflexagon. So I'm just
back in the day we had to make our own fidget toys, and to make
and I'm happy that I actually found Vihart's video, because I'll talk a little bit about kind of her class of videos itself in a second. So I'll post this link for everyone, so you don't have to follow through here. You can just do that on your own. No, I didn't want to do that. There. So on Discord, I just posted the video for the hexaflexagon. It's a pretty strange object. So I'll let her first play this for a second. We'll talk about this object. And then, of course, all of you have the link. Let's actually spend some time folding it. But let's just watch. Vihart is very famous for a lot of her doodle videos that she makes, and I enjoy them so much. So I'm really glad that there is actually a version for them.
back in the day we had to make our own fidget toys, and to make a hexaflexagon, all you need is 30 seconds and a scrap of paper, if you know how, which is probably why this is my #1 most requested video. So today I'm going to show you my hexaflexagon techniques. Now the goal is to be able to create one instantly, anytime, anywhere without scissors, tape, or glue. But to build your hexaflexa skills, you can start with a printable pattern such as this one. The essence of a hexaflexagon is 9 triangles in a twisty loop. And you can use 10 triangles if you glue the last to the first, or use 9 if you're using tape. Having a pattern is helpful for folding perfect equilateral triangles, and also it's easier to fold the finished shape if you have your mountains and valleys in a row. Dotted lines are valley folds, and dashed lines are mountain folds. And you can check that all your triangles are happy and accurate by folding them back and forth on top of each other and seeing that they all line up. The number one place people go wrong is when folding and taping the loop together. And here's where the mountain folds can help you do it right. It is of vital importance that the 3 flappy bits be symmetrically arranged all triangle-like. If you've got a flappy flap that goes all the way straight across a hexagon, or 2 flappy bits right next to each other, just try again. Then finally, tape the first and last triangle together around the edge, or sometimes you'll get a case where you tape them across the side. Or if you're using glue, then just flap that flap on over and glue that whole 10th triangle to the first triangle. Just try not to accidentally tape or glue together anything else. If your creases are strong, they will guide you in the hexaflexagon's construction and also in its use, where you pop up the center and pinch the sides together in a 3-fold way and open it up from the center. The great thing about hexaflexagons is that aside from their fidgetability, they also offer an opportunity for doodling, drawing, and decorating. And here's where this more robust fold-over design can help, especially if you have markers that bleed through your paper. It's also a great way to hide the template lines after you've made your creases. And once that's together, you can color both sides however you want to, and also the third side however you want to. Okay, so once you have a feel for that, it'll be easier to do it without the pattern or scissors. The first trick.
So just one comment. Did people get what just happened there? A piece of paper that has 3 sides. So this is a very famous puzzle. I mean, it kind of sounds counterintuitive, but it hides one of the surfaces at all times that only appears when you flip. You can go through that as a sequence. So let's just try building it first. So you guys, there is paper here. Come in, choose whatever type of a paper you want to build it. Folks can open their own laptops. You know, I think you can watch this video as many times. It is actually useful to build and get a sense for it. And once people have sort of built this, then we will really diverge in trying to make totally crazy types of things. So here is paper. I'm around. Open up that video. It's on Discord. Let's make all different kinds of hexaflexagons. And then I think we'll talk a little bit about the mathematics of that object in a second. So this, I think I can find more paper if people need. And this one, everybody should make by themselves. So at least let's make lots of them. Somebody can make a really large one. You can try making a small one. Everybody has the video, right? So I'm gonna post that in this chat also. So there is a video. And then folks that have built it, then we'll talk a little bit about what's actually going on mathematically. Yeah, feel free to actually draw on it as a pattern. There are scales. Do we have any scales? Like rulers. Yeah. Yeah, so there's a whole bunch of rulers right here. If anybody needs to draw your sets of patterns.
And this is up here if anybody needs some. And scissors and markers and crayons. Mark the bridge if they run like. Oh, yeah, yeah. Yeah.
And then folks online, if anybody has a question, you can just type it. I'll at least keep an eye on the chat while you're building it. And folks that might have just joined recently, this is sort of a hands-on day. And what we're trying to first do is build a hexaflexagon, which is on the link that's on the chat. fold it, which I find funny. So this. Ah. Ah. Okay. Oh, you guys are doing the double one now?
Yeah.
Or you have one?
One single, just the one single.
No, but it's working, right? Yeah, so the double thing is just as a way to just have hidden the creases and it looks nice. This is operational now. So you should take it and flex it.
Okay.
And this is what she was talking about, that the fold is not right in the sense that kind of the way you want to go is the mountain valley.
No, I have to.
Because so the definition of a mountain, a valley fold is proven by this now. If you compare the alternate fold, the first thing that you notice this is valley, it's like valley.
It should be.
A given surface, you have a valley and mountain fold. And now the trick in folding that is to make sure that no more than one flap is actually visible. You can see it's only a trifold, 1, 1, and 1. Unlike rather than a fold. And so that one does not flow. Because you should think of it as a sort of tape it now. So that last step is the tricky one, which is where
That's because it's not lined up. Yeah.
no, maybe that's
That's okay. I'll keep doing it my.
walking dangerous line. Next thing you know, next thing you should be.
I might have to find her way. I don't even know how to say it. But you would move on it. Oh, yeah.
And that, you ever understand where like how flows are. Now you can think. A little bit, I just did that. Really what's going on here? And then what is it? So what can you find this?
I think it's just because my mom and mom it's like you just like treat me like I was
Yeah.
When you get the correct.
like, I mean, it's not normal, but it's like pretty common. I thought it was fairly common. Like, you didn't touch at all. I thought it was like, you didn't touch. And now,
Yeah.
I'm making this a little bit larger also.
Okay.
But make a couple of these, and then of course we get into the dual one. Once this works, we're gonna try making that one.
Yeah.
It's more complicated, but I think the important thing to also just understand is how try to keep it apart. What is the mechanism of this option? What makes it work? I mean, it's a very simple thing that's in your hand, but it's not so trivial to understand what's going on. So then, think a little bit about why there are two surfaces, for example, associated with this, and what is causing resistance when you're trying to put it. You guys have one yet?
not yet.
Okay, keep going. Okay, you got it on it? Okay. Okay, yeah, you have a question. No, let's continue. That, I think.
Oh, I forget to like measure out. Maybe,
You know, I think the purpose of the video is. This is more than not having.
This is pretty flush. Okay, cool.
Once you make it the first time, the difficult to flip because the edges are not primed yet. But what we're trying to do,
Oh, wait, I think.
there are
Yo.
like some numbers here.
Holy shit.
That's why.
Yo, it just goes.
That pattern will somehow.
It gets
I just keep opening. Yeah, I think it would.
First time,
What I'm trying to do now, because of this pattern, I folded it along.
because,
I
the
can,
idea is to get,
so I'm
oh,
trying to use that pattern to like get the.
the idea is to be, it makes me matter for all of this. But it's not gonna put the date, and eventually this edge will also bend.
Yeah.
And make sure that it will bend.
Like, how exactly? I'm not sure how big the play is. Pretty good.
Out of the paper. So now.
But it's that old data. Maybe my templates some drags.
Every that I. To try finding where those things are, and continue, and I think one of the things is doodle around to see if you can understand what's actually going on. Where is the third surface? Why does it actually? And then if you succeeded in that, then the next one you can try making is the 19 one, and that has 6 surfaces today. So basically you do the same thing, except with the loss.
You're supposed to not intro.
Yeah, but I think try building a mental model for why it works. Or what is it that's actually going to be.
Right.
It's the end of the day.
See, what is very cool, right? You see that it's all the same thing, but the simplicity itself is one.
No idea.
Okay, now it's called sauce. One day is not I think this is what they call one.
If the triangle is not that, you see that the orientations of the lines that I made are not the same. I'm not going to make a pattern. It's still the same surface, but sometimes you make a pattern. And then I think the third one.
You don't like how you can also do that.
Probably that this is triangle and plan. What is what
Yeah. I meant.
try building on your head.
So, and she said, what is I?
Yeah.
It's a little bit more hard to hold, but. My hope is it's not gonna take 6 hours.
Yeah.
Okay, how are you guys doing? You have it?
Yeah.
No, that's good, but you have the long, right? So the trick with the, you have the right number.
No. We only have 8, yeah.
You wanna make, it has a name?
It has 9.
Okay, so that's good. So the idea is, mountain, valley, mountain, valley. So this is mountain and this could be valley.
Okay, I'm doing 9.
Valley.
Oh, God.
And now, the trick is that when you're comparing, that you always have only one of the lines that's open. So half, and half. Yeah, so that's the key, that there is no fully overlapping. Black. It's just be half visible triangle, half. Let's try, I'm surprised nobody made a really large one. Let's make something big. There's plenty of large paper. That maybe take that. Yeah. This is just the prototype. If you have figured it out, try making it larger, try making it out of a little bit stiffer paper itself. So that we can have some fun. And then if you are all done with it, go on the screen and you can also show the online members if they have gotten it. So this is good. Now you. And try playing around with it and suddenly how will you guys do that? Try flipping it. So I'm curious, did anybody get it? Anybody wants to show their hexaflexagons yet? Not yet? Yeah,
Yes, sir.
Ishan, go ahead. Do you have one?
Yes, sir. Yes.
It's working?
Yes, sir. It's properly working. Like,
Okay. So just the trick is, if you look, for example, at the, I'll try pinning Ishan's screen here. So if you just show that up on the screen. So just show your fold, and then everybody can see that there's a little bit of a trick, which is associated with, there should be no open flap that goes all the way across. The
yes, sir.
things should only be halfway. Anybody else? Keep playing with this. You know, it seems very simple. It's in your hand, but it's a little bit puzzling. And you know, I don't want you to give up. Try building it. There is a aha moment that will happen. And I think this is, again, the whole point. You can watch anything or read anything. The thing that I just wanted to emphasize is when you do something with your own hands, it's different. And so then try labeling the colors and see that there are actually 3 surfaces on this object. And then if you have done all of that, I just posted the document, which was the original document that Martin Gardner had described this. And it was fun to actually read that the first group of people, the history of the object is there, but the second object we'll try folding is a hexaflexagon, which now has 6 surfaces, not just 3 surfaces. So I'll just share my screen. I posted a PDF document in there, and here is the construction for that, which is instead of 9, I think this has 19. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So these are 19 triangles, but they do fold a little bit differently. So open up the PDF, get to figure 2, and then you can try folding this one. If you have finished folding the trihexaflexagon. So just the language is flexagon because it flexes, hexa because it's a hexagon, and tri because there are 3 surfaces. So trihexaflexagon. And so when I say hexaflexagon, that's 6 surfaces on a hexagon and it flexes. Anybody else on the screen online that's struggling or is trying to figure out? How many of you have gotten it? You could just raise your hands. You can just do the virtual hands. Okay, Nala got it. How many else? Dio, did you get it? Okay, and it's flipping. Oh, not yet. Not yet. So think about it. I think there is something funny that happens when you actually fold it. And the folks that have gotten it, try helping the others by just posting on the chat. The way you stick it is how it matters. Try coloring the 3 sides. And then once you have gotten it, move to the more difficult one, which is the hexaflexagon, figure 2 of the PDF that I just shared. Yeah, I think I want to make sure that none of you give up. Make sure that you actually build it. And again, the purpose of these types of exercises is to just like, you have to flex your brain to make this work. And if you finish, then you should start for the hexaflexagon. And then I'll talk a little bit about the history and then jump into what else we wanted to do today. Can I see a raise of hands of folks who have gotten it working? So I'm going to transition a little bit into a discussion at this point. If you have that in front of you, try turning your video screen on to show what you have. And then let's have a quick discussion on what gives rise to resistance and the context of the mechanical properties of this object a little bit. So if you have it, just play with it. And the question we're going to try to ask now is, so first of all, everybody understands the idea that, for example, a structure like this, there are three surfaces, one of them is hiding. Do people know where is that hiding? Where is the third surface hiding in this object? Yeah, it's in the overlap zone, right? So there are three overlapping flaps that should give rise to this. If there are three overlapping zones, it can hide total 6 triangles, right? Because there is top and bottom. So that makes a lot of sense. And that's exactly where the twist is, right? Because the object has 3 twists here. So in a scenario when it goes from the top, it goes to the bottom and comes up, you can define this as a twist in paper. So there are basically 3 twists, but those 3 twists travel consequentially as you flip, rather than the twist being here. If the twist was to move, so now whatever pattern you make and you open it, you will actually see that the 3 twists are traveling, and this is why it's hiding different areas. But now the question or a puzzle that's actually much harder to think about is you've just made a mechanical object out of a piece of paper. It does flip, but what determines the stiffness or the resistance that this object has to flipping? Because sometimes you see, you keep trying and pushing it and it doesn't go, and you press once and then suddenly it bang, it opens. So why is that? Why would it have this type of a snap where something just clicks? And again, the answer has to be sort of figured out by you guys. So play with it, and I'm wondering if anybody has any ideas. I also just broke it. More tape, please. Yes. Anybody has ideas of why does it resist to flip? Yeah.
Is it like
This is, by the way, this is live thinking. This is not something that you should just, whatever comes to your mind, you should mention. Yes.
I think your creases turn from like what they call like a
Mountain to a valley. Yeah.
So there must be
Yeah.
like some point in which that flip happens.
Uh-huh. Yeah. So one energy that I'm gonna miss the name again.
No worries. Kimberly.
Kimberly, yes. So one thing that Kimberly just mentioned is there is energy associated with bending. Remember? So any bend, we had said, although bends have low energy, they still have energy of bending. So that's true. And for pieces like paper, so one idea would be is if I make it out of a very thin material, it should flip more easily, which also I think intuitively feels, is that true in your case? When you make a stiffer, try flipping the one that's stiffer material that they have there, and then another one that's softer material. But there is something else also going on. So it's not just the bending energy. There is something else about this as a material. What else has to be true for it to truly flip? Anybody online has an idea on when you flip it, what else has to be true?
I'm not really sure if this is it, but
Yeah.
there's rubbing.
Okay, there is rubbing, there is friction also, which is good. But I think there is something even more important. So the idea to think about is cooperativity. Only one edge flipping doesn't flip the entire triangle. And so they all have to happen simultaneously. And this is why when you're pushing, and then you push the last one. So somehow these edges are talking to each other because they're topologically, you've connected them. So if you think of them as linkages, you have created a type of a linkage. When you create a type of a linkage, there's only a certain degrees of freedom. And so unless you are flipping all of them simultaneously, the other linkages resist. So when you create many origami-like structures, that's why they have some really strange properties. So it's not so different from the crumpling paper idea that we talked about. In crumpling, all of these edges are folding, and then many of those folds are incompatible. And that incompatibility is what's giving rise to resistance and physical force. And similarly, in this case, the three edges, the three folds that have to flip from one side to the other, all have to be happening simultaneously. And this is why when you're doing, it feels almost like you have to be doing that action simultaneously. So the resistance of that material is actually arising from the fact that you've created a kind of a link between them. And so many origami structures will have this because you push somewhere and then you see action far away, right? I mean, I'm sure you've all done the swan. You push on its tail and the wings flap. That's because many of these folds are linked together in a way. And it's not so trivial to write this down in a method of linkages, because, you know, linkages that we will probably talk about when we talk about compliant mechanisms, you can write this down mathematically very easily. But in this case, at least one important thing to remember is that you can create a structure that has connectivity, and the connectivity is what drives its mechanical properties. So maybe as a closing, and I'm just realizing I didn't know that it would take so much time, but maybe that was an important thing to do because I want you guys to realize that everything that you read and see might sound trivial, but unless you've done it, you haven't encountered that phase of what it means to do something. So just keep that in mind. Another rule of thumb is whatever you're trying to do, multiply that by time of pi. That's how long it takes to actually do it. And so we've run out of time. But I'm curious, as a homework, just like for the homework for the back of the envelope calculation, what homework do you guys want to create for yourself? So given all the materials that you haven't had the chance, we can just go as teams of 2. You guys can spend maybe 5 minutes talking amongst each other, and then come up with one thing that you would go back and build out of a piece of paper broadly defined with origami broadly defined. It can have tape, cuts, anything. It can be much more function, or it can be something that you just want to implement because it's fun. So, and online, one things that would be valuable is folks on the chat can also start writing anything that they would like to build, and try challenging yourself. So if you already know how to make it, that doesn't count. So the whole point of all the assignments is that they need to be open-ended. So we can take 5 minutes. People can talk in their teams a little bit, and this will be a team exercise. So folks that are in groups, and try coming up with something that you might actually want to build. On the online side, I think let's just do that as a one-on-one, and people can start typing. This is, think of it as your dream origami. If you give yourself a day, what would be the wildest thing that you want to make out of a piece of paper that you don't as yet know how to make, but you're going to work on trying to make something like that? And then I'll keep an eye on chat and kind of give feedback and other things as well. And I'll be right back. I'm going to just go talk to the teams.
After you said that, I you stick all your fingers.
That's it. That's it. That's coordination. So then you're providing the feedback to every one of the kings simultaneously.
Oh, wait, yeah.
Yeah.
Yeah. That's cool.
Yeah. I mean, you know, it's only a property of topology and geometry. It has nothing to do with the physical properties of that material. It is very interesting. Many a time, like the thing that we were talking about, 1400 times its weight, that sounds absurd. Where does that strength come from? It comes from the linking many of these structures together So eventually it's the same thing, but suddenly unless all of these things are, and there must be a weak point in that system that if you perturb it one way, that the whole thing collapses.
Yeah,
It's the same idea.
yeah.
Okay, so what do you guys want to build? You have a week to make something crazy. What would you want to make?
Collapse.
I think something like,
Or like,
well,
I just like the idea of
Okay, water is good. Yeah. Yeah, what's really fun about floating on water or oats that you've all made oats, they take in water. And then suddenly the bottom material is actually soft and the top is dry, which is stiffer. You guys could make something that you put on water and turn it into steam. Your origami changes because you put it in water.
shape shifter.
Okay, I think that's a really fun goal. And I like the idea that you just explore materials that are partially wet and dry. And what's really fun is that that gradient can be very complex because when you put it in water, it's folded. So patches that are not contiguous would be wet.
Right.
Right? I mean, it's not just if I put, so what people have studied is, if I take this piece, there are typical types of pieces of paper that you can put on water and they will curl up. And what happens is this is wet and this is dry. That leads to what is called biaxial strain. And so then this is softer and this is stiffer and that leads to a rolling. But what you guys are thinking about, so you should first try that. Try finding the paper for it. I think it's from Gideon Risset at Harvard. They did these experiments of just floating sheets on paper that roll up. And actually it turns out there is a Japanese food in which this also happens. You guys know this type of a ginger flake that they put in the very end, and that happens with the heat. One side is hot and one is cold, and then so when it moves in your plate, I mean it's not alive.
Like there's people like apply for helps and they
Thermal.
like
Yeah, so that's also a biaxial kind of strain. But what would be fun is if you immerse something that's folded and that's put together, then that's different because that changes the patches. So if I want to fold something like this, for example, and immerse it in water here, this zone is wet, but if I unfold it, that's actually patches of wet zone, so it's not contiguous. Okay, I think you guys have your own assignment.
Okay.
1 week's time. Okay, what do you guys want to make?
Fine, yeah. I was inspired by.
It's like
Okay.
3 hours.
Yeah. So what you could make that? Something
But like,
stand on. That would be pretty cool. It has a base, and one thread then is to think about motion.
they took a bunch of ranges.
We come up with a pattern that's not better than they.
Native.
You have to do something new, right? So I'm okay with you for starting somewhere, that's
And
all good.
reveals like the water.
It's a dimension that does something.
Because the pavers, water, outer buildings.
Something.
And it makes it so big.
But also.
I
I was thinking.
And so it slowly disintegrates.
Yeah.
There's a lot of fun there.
Maybe. So, I mean, I think one side of that is, this one has the origami that. You should practice with that with flour. One of the goals is to using the goal pushes you to think deeply rather than just repeat it as an exercise. This is a very important one because it seems simple but has very deep ideas. You can use that to prime yourself, but make sure that anything that you choose, you're doing beyond what you find.
Oh, yeah.
Right? So if you can start with simple app, find one example and say, oh, if I wanted a high performance ratio.
Yeah.
You think about strength. What I'm hearing is that this thing has to move. The origami has to move, right? And I think you guys have a good. Okay, what you guys gonna make?
Somehow make it, but. Like, I think if we.
All materials. Then,
Like some sort of super like. You have to.
make up origami, right?
Like.
Not at risk of conflict there. I like the idea that.
Right.
Order power, and it's perfectly okay to have. Electricity, or whatever you want. Okay.
And
so you have that.
yeah. It's not able to. Like it breaks apart, and so that's the only thing. Right. It's like, if you like, yeah. So one thing we had. Yeah. That should have to be.
Yeah.
So we all have to wait for one thing.
All right.
What do you guys want to make?
Right. I like it. I love it.
I don't know, how, like, I'm curious about speaking for a year, for like, more probably. Wait, that.
How to create something new. And have a metric or a dimension that you can measure. If you say that, oh, I think one thing that is funny is that you said that if you put on there's lots of examples of those types of things. And then you can try finding another way of doing something like that. It's perfectly okay to explore that space, but the idea would be is that then you come up with a fold or a type or a mechanism that does that. Whatever you commit to now is not the end game. You guys can. But you have a lead, but define the goal. Have a clear definition of what it is. And then go and then in a week's time, present. It doesn't have to be.
I think so.
Just want to share the whole process of how. Okay, all right.
If you can like play around with some stuff as breaks, this weekend. Yeah. And then.
You guys know what you want to do? And then be your time.
By extension, like, hope you both do that. Yeah. But when it's wet, and it's like, and the thing.
Storing energy.
Yeah.
this thing goes into fourth outward, right? And if you had two of these things identical but flipped, it doesn't matter. This like, it explodes. Circular
Well, young.
I can imagine.
Doing something like that going on. And you know, try doing things that are hard and you don't know how to do it. Because
I mean, I'm fine making that determination.
And I love the idea of storing energy. I mean, frogs are all designed that way, but they store very little energy. So like, if I think, oh, this one is gonna jump much higher than any other origami.
Somehow like that.
So I think I just spoke to everybody here. Looks like everybody has a project. You have 1 week's time. And so on Friday next week, people should bring their sets of things. Try sharing what you're thinking about on Discord. I'm now looking at some of the chats to see. Okay, let me go all the way up. This is exciting. Thinking about a turtle. Nice, cute animals. That's good too. Transforming paper cube. I like that. So I think what maybe Ishan, what you are referring to, if I try to translate, is this idea. The hexaflexagons are flat structures that are transforming. Could you actually do that with a 3-dimensional structure that still transforms? So that would be really fun. Omega stars and origami manipulator. I absolutely love that. I think lots of you have seen in the last couple of years a lot of robotic manipulators, but completely made out of single sheets. A kinetic paper sculpture, Muriori. Curious about insects, butterfly wings. If people are interested in wings, you could try making a version of beetle wings, because beetle wings actually fold. So you could try coming up with, I don't know how many of you have seen this, beetle wing origami folds. You know, we're not the only people, or actually another way of saying this, insects discovered origami long time ago. So right here is a
snap of the wings tips this overturned beetle upright. It then performs some hands-free origami to retuck its wings.
Do you see what's going
Scientists didn't know how a wing strong enough for flight could fold so neatly. The ladybird beetle keeps its hind wings sheathed when
on?
walking,
Sucked in.
lifting the spotted case, called elytra, to unfurl the wings for flight. On landing, the wings pack themselves away.
You see what's happening? It's
Since the
self-folding
wing folding
origami.
process is hidden
Every
under the
single
elytra,
time it flies.
scientists replaced part of the case with clear plastic.
That's both
So you
sad
could
but
peek
also
at the wing
cute.
in motion.
That's hilarious.
They tracked how the wing bent into itself like a Z
You see that they can actually see what's
and
going on.
documented the 3D shape with X-rays.
Oh, that's beautiful.
Thick veins work like tape springs. They
So-
store energy for quick deployment and stiffen to provide stability for flight.
I'll leave that here. There's a lot of work in the past that we have done on beetle wings. And what would be fun if somebody's excited, try making a paper only, or maybe paper plus some rubber-like material as a mechanism for replicating what the beetle is doing. And the reason I'm just mentioning this as a context is the purpose of this 1 week exercise is to not just do what you already know how to do. So Tafia, this one is on you. Now I know the name, so I'm gonna call out on you to think about it.
I mean, that's a beautiful idea. But remember, the purpose of the exercise is to take on a challenge that you don't know how to do as yet. Vivek, something like an umbrella which opens itself when sunlight falls. I love that idea. So then you're suddenly thinking about incorporating origami and sort of solar energy and heat associated with it. I think heat actuated origami by itself is really fun. Origami hat, that's really fun. And I know it's coming from DU, so this is going to be a serious, fashionable hat, knowing him. Paola, I'll try making a dog. Crestling origami. And I think crestling is a really fun thing. If people don't know, these are self origami structures that form purely by collapse. So crestling origami has this very interesting shape where you don't actually make the origami, the paper makes the origami itself. So we'll see whether, I think this is one example of crestling origami.
Look closely at the natural world and
I want to make sure I'm sharing the screen for a second.
look closely at the natural world and it'll unfold around you, literally. Take the way plants grow and develop. They look like delicate pieces of origami. Yet these patterns govern more than biology. A simple experiment proves it.
Right there.
Now I have to concentrate. Fold in the opposite direction. Not bad. Almost perfect.
The folding pattern was created spontaneously, without an origami artist or any sophisticated hand folding.
It was created by the use of force.
You understand what just happened?
And so pure physics was able to unfold in this system.
There was no lines, there was no crease, nothing. And it's a
Here's
hidden
another
pattern.
example.
This is a really fun one.
With these crushed paper cones,
See that?
we have created an instant origami object. It happens impulsively within a second.
The result is striking. A logarithmic spiral, typical of the patterns found in nature, was formed spontaneously by a piece of paper on a desk. Origami appears to be woven into the textures of our world.
Okay, I'll leave it here. But again, as you can see that there's an infinite amount of exciting things that you guys can all do. And what's very valuable is whatever you pick, try pushing yourself. First, replicate what has been done in that space a little bit. But I mean, the beauty of what we are doing and what I wanted to be playful is the way Chrisling discovered it is purely by accident. She's actually an architect, and now she has an origami named after her. And it was a pure accident. It was not some rational thing that she was after, this idea of self-folding origamis. She was just twisting cylinders and she saw this. And finally, also the hexaflexagon that you guys just saw was actually discovered by a student in UK, but he was American. So he took his notebooks that are American, that are a little larger in size than the UK paper. And so to make it fit, he was cutting edges of all of his paper, which is American size to fit the UK format. And he had these long strips lying around and he was just trying to fold them into triangles as a doodle. And suddenly he noticed that this thing flips into 3. And that actually led to what we just played with today and an entire branch of mathematics. And ironically, around the same time when he was an undergraduate, Feynman was also an undergraduate and was his friend. And Feynman, Tucker, and several of them started what became, it's all in that Martin's article, a flexagon committee or a club. And on campus, everybody was, it became the fidget spinner of that time. And it would be fun to revive it. So share and teach your friends how to make hexaflexagons. But what would be valuable is just remember this idea that, sometimes you just have to play to make interesting discoveries. And I'll talk a little bit about in the next class of how to just, when you make these types of, and you have a bag of tricks, how do you use them in the problems you're trying to solve? But unless you don't have a bag of tricks, you're not going to do anything that's new. So you have to use your muscle to come up with a bag of tricks. So keep that in mind. You might be very application focused, but if you don't have a bag of tricks from around the world, you don't know how to actually do something that's very different from what others would do. Okay, so we're going to close on that note. Good luck. This is going to be a 1-week assignment, and I'm really hoping you guys put your heart into it, because if you don't try anything, then, you can listen as much as you want. It doesn't change anything. So until next Tuesday, see you guys in the class. And then when you have an idea, try sharing it. Because as a class, what we're trying to do is to try to do things collectively. So if you have defined your project, just write it in Discord of this is what I'm going to try to do. See you next time.